Today, we will introduce a very important area of machine learning, which is unsupervised learning. So, in the previous courses that we have introduced several supervised learning methods, including, for example, the regression methods, and also support vector machines and also logistic regressions. So these methods can be used to process or analyze the data with non-labels. But sometimes we will have data that with unknown labels. That in this case, that we want to classify our data into different subtypes. So that is the cluster analysis is all about. So today we will divide the course into two parts. The first part, I will introduce the basic of cluster analysis and, for example, the K-mean clusters. In the part two, I will introduce a specific type of distance measure that can help to define the relationship between different types of data. Okay, so let's move to the first slide. Okay, so I want to recap the methods we have introduced in the previous lessons. So basically, the machine learning can divide into supervised learning, unsupervised learning, and also reinforcement learning. And the last type of the machine learning is quite similar to the human. So we all learn from mistakes. So if we can improve the machine learning model by learning from mistakes, that would be very powerful. But for now, that we will focus on the supervised and unsupervised learning. So as I said, the unsupervised learning is mainly the data-driven technique. The purpose of this supervised learning is to identify clusters in the data. So in contrast to the supervised learning, which is the task-driven, then we will try to predict the dependent variables based on some predictors. So that is the major difference between these two techniques. Okay, so for the unsupervised learning, then and there are many applications that we can do the feature elicitation. We can do the structure discovery. We can find a meaningful compression or information using a cluster analysis and visualization. And also we can do the customer segmentation and to find out different type of customer. For example, in a certain business, then we will identify a subtype of customer. Then we can do the targeted marketing. So that is the quite a common applications that of cluster analysis in the business. But today we will focus more on the medical applications. So this is a quite intuitive presentation of the cluster analysis. So suppose that we have a raw data like this. Then we have 3 blue circles and 2 red circles and 2 gray circles. Then we hope to develop an algorithm that can classify these raw data into different types of output. For example, we want to cluster these blue circles into a group. We also want to identify 2 gray circles into one group. And likewise, we also want to identify the 2 red circles into one group. So this algorithm will help us to cluster these raw data into different types of output based on the similarity. So in this case, the similarity is defined by the colors. So the same colors will be grouped into the same cluster. So that is the idea of cluster analysis. So the one of the important concept behind the cluster analysis is to measure similarity. And these similarity measures is a set of rules that serve as criteria for grouping or separating items. So for example, in the previous slides, the rule would be the color. But there are many other rules that we can define. So that is quite intriguing because sometimes we need to define good rules to find the good clusters. I will talk about this later. But basically, we can have two types of the similarity measures. So one is the correlational measures, for example, the Pearson correlation. So we have two data that we want to, then we can measure the correlation between these two data. For example, if we can measure the brain activity in the two different brain regions, then we can measure the correlation between the brain activity of these two regions, and then we can use Pearson correlation to define that correlation. So this is one way to measure similarity. But more often now we will use the distance measures in a cluster analysis, because the distance measure is a matrix that to define the distance between two data, and the higher values indicate the greater distance similarity. And for example, we can measure the Euclidean distance on the two-dimensional map or in a three-dimensional space, or even a high-dimensional space. Or we can measure the angle between two vectors, and if the angle is very small, then suppose that these two data or two vectors are very close. So distance measures can be many, and also in the correlation measures there are also some variations. So these are two types of similarity measures. But as I said, for the cluster analysis, it is mostly based on the distance and proximity measures. And for the distance measures, the higher values is corresponding to the last similarity, and is opposite in the proximity measures. But for the factor analysis, which is a very important statistical techniques in the data analysis, then the factor analysis is based on the correlations. It's based on patterns. So I want to show you one figure to illustrate this concept. The correlation is a measure of the patterns, similarity of the patterns between two data. For example, here we have orange data and blue data, and you can see that they all have the increasing values until the 5 and decreasing until the 7. The difference between the orange data and the blue data is that it has a higher values in the orange data and the lower values in the blue data. However, if you look at the patterns, you will see that the orange patterns and blue patterns are very similar, because if you apply the Pearson correlations to these two data, you will find a perfect correlation coefficient between the orange data and blue data, no matter in this case or in this case. But however, you can easily see that there are differences between these two orange and blue comparisons. For example, the distance between in this case is smaller than that in this case. So So that is the major difference between the correlation and the distance. The correlation measures patterns, and the distance measures the actual deviation from one data to the other. So if you want to look at the factor analysis, you want to look at patterns and correlation analysis. And if you want to look into, for example, the many parameters in a set of data, then you probably want to measure the distance. Okay, but for now, then we will focus more on the distance than the correlation measures. And one of the two types of the cluster analysis is the hierarchical and Kmeans clustering. And the ideas behind the hierarchical cluster analysis is that it's trying to use the tree-like structures to divide the data into different groups. And in contrast, the K-mean clusterings try to draw and try to give an envelope to define a group of the data. So these are all cluster analysis, just two different methods. And in this, the first part of the course will focus on the K-means clustering because it's very easy to understand and also it's very powerful. So, but there are many other methods that is related to the hierarchical clustering. Then we will talk about this more in the second part of the course. Okay, so the basic idea behind the K-mean cluster analysis is that if we have the data like this one, then probably you will see that, okay, these are one cluster, this is a second cluster, this may be another cluster, but we want to develop an algorithm that can do this kind of job automatically, and we will derive the results like this one. So we have a 1, 2, 3 clusters, and that is the algorithm we want to develop. Okay, so let's just move right into the K-means cluster analysis. The word K here, the letter K here means how many clusters we want to define. So it is very important to know that there is no prior knowledges that can there's no algorithm that can tell you the true number of clusters. And most often we need to arbitrarily to define the number of clusters. So that the K-mean cluster means that you need to define, the first thing you need to define how many clusters you want to separate your data. So in the step 1 of the K-mean cluster analysis is try to choose the number of K of clusters, meaning that for example, you want to divide the data into 2 clusters, which is K equals to 2, or you want to divide the data into the 3 clusters, then you will select the K equals to 3, and that is the number the letter K means. Okay, so the next step is you need to try to select the random K points as a centroid. So the centroid is a measure that tries to find out the center of the data. And there are some methods about centroid, but most of the most intuitive way to understand centroid is about the physics. So if you have for example, in a solar system, we can determine the centroid of the solar system by weighting the mass of each object, for example, the mass of the sun, the mass of the Earth, the mass of the Mars and other planet, then we can weighting this the mass to find out the true center, the balanced center of this solar system. So likewise, in the if we have many data points, then the first thing we need to find out, select how many the k points, then we put it on this the data space. Then because we choose the number k as our number of clusters, so the first thing we need to do is we try to put the random k points as the initial centroid. That is not necessarily the true centroid, but we just put the random k points on this data space. And then we will assign each data point to the closest centroid. Then, and the next step is try to compute and place the new centroid of each clusters. So once we assign each data point to the closest centroid, then we will have the first result of the clusters. But that cluster is not optimized because we need to, the first thing we need to define the centroid and to find out if that centroid is not reasonable or not. So maybe we can find out a new centroid that can more reasonably define the cluster. So that is the K-means cluster all about. Then, so using the iterative process between the step 4 and step 5, then we will reach the final results if any reassignment does not occur. So that is the point when the analysis is done. So probably you cannot follow me just based on these descriptions. So how about that we use some visual example to show this idea. So suppose we have the 9 data points. Then it has 2 parameters. One is on the x-axis and the other is on the y-axis. And for sure, then your data may have a higher dimension. Means that your data may have more than 2 parameters. Then, but in this case, just for visualization, then we define our data to have 2 parameters. One is a plot on the x-axis, and the other parameter we will use this as a y-axis. So suppose we have 9 data points, then we want to find out how many clusters in this data. Then the first thing we need to do is choose the number of clusters. So you probably will say that, okay, it seems that it has the 1 clusters here, 2 clusters here, or 3 clusters here. Or maybe you will say, okay, this is 1 cluster, this is another cluster, just based on our brain. But that is a tricky part, because if your data is very complex, and for sure you cannot find out the number of clusters just by looking at the data. But for this case, you probably will generate your assumptions of the number of clusters. So here, how about we just choose the number of 2 clusters just for simplification. Okay, so the step 1, we just choose the 2 for our k. And so in that case, then in the step 2, we need to randomly put 2 points as the centroid. So as I said, this 2 data point is not necessarily the true centroid. We just need to put the 2 data points as an initial centroid to help us to determine the clusters. So for example, we put a green dot here, and the red, the blue data points is here. Then we just assume that this is the initial location of the centroid. Okay, and the next step is we need to assign each data point to the closest centroid. So look at this key term here. The key word here is closest centroid. It means that we need to define the distance between the data points to the initial centroid. Then we need to find out which centroid it is close to this data point. Then we will give is one of the classification. So for example, initially we don't know the clusters of this data, but because we define the centroid here, then we can assign this data to the green centroid because it is closer to the green data point, green centroid, than its distance to the blue centroid. And likewise, if you look at this data point, and this is closer to the blue data point or blue centroid rather than the green centroid. So you can easily try to make a line between the two centroid and make just another line just perpendicular to this line, and to dividing this line into two equal parts. So that is the one way we visualize which data point is closer to which centroid. So using these methods, we can easily identify these three data points are closer to the green centroid than those distance to the blue centroid. So they belong to the green clusters. And similarly, we can assign these 6 data points belongs to the blue centroid or blue clusters. So this is the results from the initial location of the centroid. But of course, this is not the optimized solutions. So the next step is we need to find out the true centroid within these clusters. For example, we have these 3 green data points. Then we need to find out the centroid of these 3 data points. Then we'll move the initial location of the green centroid to the actual one, the centroid here. And likewise, we will also calculate the centroid of the blue data points. Then we will move the blue centroid to the new locations according to the blue data points. So that is the very important step, because now we have 2 new centroid and they have different locations. Then we need to redo the clusters by just try to find out the line perpendicular to the line connecting these 2 centroid. Then in this case, you will find that, okay, this one was originally belonged to the blue clusters, but now because we have recalculate the location of the centroid, so this one will be reclassified into the green clusters. So because we have a new assignment of the data points, then we need to recalculate the centroid according to these new clusters. So we need to calculate centroid of these 4 green data points, and also we need to recalculate the centroid of these blue clusters. So immediately you will find out that using this kind of iterative process, then we can reach ideally, then we can reach an optimal solutions that can divide the data into these two clusters. So that is the very essential ideas about the K-mean cluster analysis. It's a very elegant algorithm, and in an ideal situation, then probably you will find a very good results just using this kind of iterative process. Okay, so let's recap the whole algorithm of the K-mean cluster analysis. So in the first step, then we don't know the cluster patterns of this data. Then we'll just, for example, we decide that we want to divide this data into two clusters. Then we will put two random data points on this data map. Then we will calculate the distance of each data point to each centroid, and to determine the first classification results. And then we will calculate the true centroid of these clusters and the another cluster. Then we readjustment our result, and in the final step we can find out, okay, these are a result of the first clusters, and this is a result of the second clusters. So that is it's kind of iterative process that can try to find out the data structures of an unknown labeled data. So I hope you can understand this process. If you still cannot catch the idea, so just try to look at the PowerPoint files and try to understand the whole algorithms. Okay, so probably you will think that is that too good to be true, because for every kind of the applications, is that really 100% chance that we can find ideal clusters? And the answer is, of course, no. So there are some situations that this K-means algorithm cannot find optimized solutions. For example, here we have a visualization of probably 3 clusters of the data. So this is one group, this is another group, and this is definitely another group. But probably you will say that this is maybe one group and this is another group. There's no clusters dividing these two groups. So this is just one group. So that is the tricky parts of the cluster analysis. For example, if you just put the 3, let's say if we want to divide the data into 3 clusters, then you select the random initialization of the data, the centroid. Then if you just put the centroid in these positions, then probably you will find out the 3 cluster you expect to see. And so this is the ideal location of initialization. However, if the initial locations of the centroid is not ideal, for example, in this case, you put the 2 centroid in the same clusters, then you will never find out these are 3 clusters, because these centroid will never goes away to the other clusters, because it can. If you look at the whole algorithm, one of the important steps of the K-mean algorithm is to find out the centroid. So it's easy to see that this red centroid can never be moving away from these clusters. So that's why for this one, it will trap into these clusters and will never be able to identify these actually are two clusters. And likewise, in this case, we will always find out there are two clusters, but actually there are just only one groups in these areas. So the selection of the initial location of the centroid is very essential to your final result. And so this is, we call that a random initialization trap. And the solution to this trap are many, but there are two common methods that we can try to overcome these limitations. And so this is one of the methods we call the K-mean plus plus. So the idea behind the K-mean plus is that never choose the centroid in the very closed manner. For example, in the previous in this case, the distance between this centroid is not quite homogeneous, and in this case, the distance between the clusters are maybe just ideal situations. So if you find out that, okay, you can calculate the distance of each data point to this centroid, and in this case you will find out lots of the data points have a larger distance to these two centroids. Compared to this one, the average distance from the data points to the centroid is quite small. But in this case, you will find out that the distance to the centroid is quite large. So the idea behind the K-mean plus plus is that you try to find out the centroid location, the position of the centroid in a quite sparse way, meaning that they cannot be too close to each others. So for example, if you put the first initial centroid here and the second centroid here, then the third one should not be very close to them. It should be away from these two. So it will ensure that we have the centroid in a quite separate way or sparse way. So if you want to know the idea behind this, you can look up into this web link. Then it is written in Chinese, so you can more easily understand the background of the K-mean plus plus. And if you want to find out the English resources, just type this on the Google, then you will find many English resources. Okay, another solution to this random initialization trap is the iterative self-organization data analysis technique, which is abbreviated as ISO data. And the idea behind ISO data is even more intuitive, because if you find out the cluster like this one, cluster A and cluster B, then you just try to measure the distance from each data point to probably maybe the centroid. So in this case, you will find out the distance to centroid is not homogeneous, and it has a very large standard deviation, meaning that you should separate these clusters into two groups. So the idea behind the ISO data algorithm is that it's try to merge clusters or separate clusters based on the within clusters metrics. For example, if you find out that within cluster metrics to be have a large standard deviation, then you will need to divide this cluster into the subclusters. So that is the solution that to ensure that you have clusters with quite a homogeneous standard deviation of the distance. So that is the second solution. And I hope that you can understand these two concepts, and then you can find more resources on the internet yourself. Okay, so another important issues about the K-mean clusters is that how many clusters we should define. So that is a big question, because, for example, you can define that you just only want to find out 2 clusters in this data, or you will think that maybe there are 3 clusters in this data, but what numbers is optimal, and that is the big question. So here I just want to show you one simple solution, and there are many other solutions that you can look up into the literatures and or web resources. But here I just for the teaching purpose, I want to show you the simple solution here. So for this data, then for example, if we define there are only 1 clusters, okay, so then you will probably want to find out the centroid based on this only 1 clusters. And if you put the centroid here, then you can measure the distance from each data point to this centroid. Then you can sum up the square distance of all these distance measures between each data point and the centroid. So in the case of the k equals to 1, meaning that you have only 1 clusters, then you will find out the results of the within cluster sum of squares by calculating the distance between each data point to the centroid, but it's a square distance, okay? Then in the case of the k equals to 2, then you will calculate the within cluster sum of the square distance by calculating the distance between the blue data point to the blue centroid. And likewise, you will also calculate the distance between each green data points to the green centroid. Then you will also find out the summation of the within cluster sum of squares. And for example, if you can also calculate this matrix in the case of k equals to 3 or 4 or 5, and then you will divide you will find out this kind of relationship. So the horizontal axis here is the number of clusters, and the vertical axis is the within cluster sum of square distance. Then I just cite this figure on the internet. It's not the results from the previous case, but however, I want to show you in this slide. It's called the elbow methods. So you can imagine that if there is an optimal number of k, then this within cluster sum of squares shouldn't be improved further after this optimal number of clusters. So it's just like an elbow. We need to find out that a point that has not much substantial change when you increase the number of clusters. So in this case, you will think that, okay, this is probably the elbow points, which means that in these points, it has no further substantial change in the within cluster sum of squares. So we can define the optimal number of clusters to be 5 based on this profile. But I want to emphasize that this is only one method to determine the number of clusters, and there are other methods that to determine the number of clusters, and so I also want to you to look into the resources on the internet. For example, you can click on this link, and then you can understand the other methods to determine the number of clusters. But the elbow point method is quite intuitive and is very simple to understand. Okay, so I hope you that already understand the concept of cluster analysis, and you probably will be wondering that, what do we do with these methods? So the cluster analysis is used for the data reductions. So for example, a researcher may be faced with a large number of observations that can be meaningless unless classified into manageable groups. And this is quite common or typical in the clinical trials, because in the clinical trials we have a large number of the participants, but oftentimes we just using statistics to find out to verify if, for example, if a response of a certain drug is meaningful in these large groups. However, we know that everyone has a different genetics profile and has a different, maybe the metabolic expression profiles. Then certainly these different metabolic or genetic profiles can influence the response or efficacy of a given drug. So in a clinical trial, we usually want to find out subtypes of the patients. And in that case, then we will apply the cluster analysis in this kind of situation to find out the manageable groups of the patients that can maybe have different profiles of the efficacy or the adverse effect. So that is the purpose of cluster analysis, to use for the data reduction. And it will be very helpful to generate a hypothesis. So the hypothesis generation is also one of the advantage of the cluster analysis, and it is very useful when a researcher wishes to develop hypotheses concerning the nature of the data or to examine previously stated hypotheses. For example, if you think that maybe schizophrenia have a different subtypes, then you hypothesize that the different types is related to the cognitive functions, then probably you will try to validate your hypothesis by doing the cluster analysis based on the cognitive functions. So that is another useful purpose of the cluster analysis here. But probably the most important and most often used application is to try to identify the relationship between different data. Okay, so for example here I just show you one interesting study. They try to try to make a cluster analysis of a genetic expression profile of different parts of the garlic. For example, they have in the garlic, when it has a bloom, that you can see the flowers, and you have leaves and cloves and a basal plate and roots. And just like our body, then in each part of the garlic plant, they will have different genetic profiles or different genetic expression profiles. So if you can measure the genetic expression profiles of different parts of the garlic, then you will use the cluster analysis to correctly identify the different parts of the planet into different clusters. So for example, the basal plates and roots are clustered together because they are closed, and they're also close to the cloves and leaves, and they are closer, but the flower and the inflorescence are more close to each other than the other parts of the garlics. So that is one important application is for cluster analysis, try to identify the relationship between the data. So I will show you more examples in the second part of our lectures. But before that, I want to show you some limitations of cluster analysis. So one limitation is that the cluster analysis is really a descriptive technique rather than inferential technique. So what I mean is that the results of the clusters are qualitative. It's not quantitative. Maybe in some cases we can do some quantitation, but in most cases the cluster analysis can only give you a descriptive ideas about the data. And the problems of the most cluster analysis is that the number of clusters are arbitrary. Then you need to verify these clusters by the other supporting data. And so that is, you need to be very careful because you can easily do the cluster analysis, but you need to be very careful about the interpretation of your clusters. And it's also very important to know that the clusters, the results of clusters are totally dependent upon the variable used. For example, if you have if you have a genetic data, you have a physiologic data, then also you have the brain imaging data, then you want to cluster the patients with the psychiatric disorders into different groups. Then you need to know which variables you want to use in the cluster analysis. If you use the genetic data to do the clustering, then of course the results will be based totally on the genetic data, not on the physiologic profiles or on the imaging profiles. So you need to really be careful about what the data you are using to do the cluster analysis. And that will be totally determine your results of the clusters. Okay. So for example, here I want to show you one classical studies try to divide the psychotic patients into different subtypes. So in a psychosis, we usually have a diagnosis of schizophrenia or schizoaffective disorders or bipolar disorders with psychosis. So the difference between these three groups is that the schizophrenia has more profound the cognitive decline, and they have profound delusions and hallucinations. But in the other side of the spectrum, psychotic spectrums, is the bipolar disorders, and which has cyclic patterns of the mood, episodic mania or depression, and at the same time, they will have psychosis during the mood episodes. But sometimes we'll find out there are patients that has a mixed features of schizophrenia and bipolar disorders, meaning that they have a psychosis, continuous psychosis, but also the intermittent mood episodes that cannot be explained by the psychosis itself. So in this study, they believe that this classification is not very accurate. So they want to find out other classification based on a certain variables. So in this paper, they select the brain. They call the cognitive function the brain-based biomarkers. It's not actually the imaging marker. It's neither imaging nor the EEG markers or physiological markers. It's just a cognitive measures, and so it's reasonable that you can see that if you use the cognitive variables to classify the psychotic patients, then you'll find out 3 clusters. They also use the K-mean cluster, so they define the K to be the 3. Then you find out that in this biotype 3, in this cluster, they have more bipolar patients than the schizophrenia patients. And in the cluster 1, they have more schizophrenia patients than the bipolar patients. So it just means that in these clusters, they have a more cognitive decline because they have more schizophrenia patients in these clusters. And in this biotype 3, it has a better cognitive function. It is because they have more patients are bipolar disorders. So sometimes we need to think about the results. So maybe it's very fancy to call this classification biotype, but actually these are results of the cluster analysis using cognitive functions. So if you are using the imaging markers as variables to do cluster analysis, probably you'll have a totally different results. So that is one of the limitation, but also the beauty parts of the cluster analysis, because if you choose the right variables, then you will have a very good solutions. But if you choose the wrong variables, then you probably will get the meaningless results. Okay, so in the final slides, I want to show you a very useful tool developed by a Taiwanese researcher, which is Professor Chen Junho. He is a professor at the Institute of Statistical Science at Academia Sinica in Taiwan. And he has developed a method called Generalized Association Plots. It's a very useful software to visualize the clusters of your data. So in this software, you can choose the different types of the measure. For example, you can choose the correlation measures. You can choose the distance measures. Then you can input your raw data and they will visualize the clusters for you. So I find out this is a very useful applications and software that can help you to do the cluster analysis. Okay, so I hope you enjoy this introductory lectures about the cluster analysis. Then in the next part, then I will show you a special application that I have developed quite a while ago, but it's a very interesting application. So it's also a very elegant application of the cluster analysis. So see you in the next part, and bye-bye.